All right, so we'd alluded in previous video that the electron configuration that elements and ions want to achieve is the noble gas one. They want to have this nice, perfectly filled shell that the noble gases have. Um, and I'd mentioned that I'd alluded or foreshadowed to that really having a name that we call the octet rule. And so let's formalize the octet rule here. We'll talk a lot more about it in the next chapter, but I just want to give you a quick intro. The octet rule really means that main group elements, and by main group we just mean not the transition metals, so not this big chunk here. Those abide by their own wacky chemistry. But main group elements, they react to have 8 valence electrons. 8 valence electrons are going to be the S2 filled and P6 filled, right? Which would mean the same as the electron configuration of any of these noble gases here. So the octet, any element on the periodic table aside from the transition metals, are really striving to achieve noble gas configuration, which is the same as achieving 8 valence electrons. They want this full s and p orbital here. So the octet rule is really used to rationalize the behavior of some of these key groups here. So if we look at 1A, which we're really familiar with now, that's got that very low ionization energy, meaning it's easy to pop that electron off. And the reason for that is because it's got that NS1 electron, right? There's an S1 here. It's easy to steal that thing, and when you do, then you give it its full octet rule, meaning you bring it back to NS2 NP6, right? Then it becomes the octet rule, it becomes the noble gas configuration. Same is true for 2A, right? For beryllium, magnesium, calcium, strontium. We have low ionization energies for the first 2 ionization energies, because once you pop 2 electrons off of any of those group 2A metals, then they also have this nice closed shell NS2 NP6, depending on what N is. That just depends on what level or what row you're in here. But they're all going to be closed shell noble gas configuration. So if we jump over to 7A on the other side of the periodic table, we said that's got a really large negative electron affinity. Remember, electron affinity is the energy that's released when you pop an electron on, when you add an electron. And that makes sense, right? Because all of these elements in group 7A and the halogens, they're 1 electron away from achieving the full octet, that full NS2 NP6. So if you give it an electron, it achieves this, it's happy. So everything is striving to get to this happy octet. I should say octet comes from the word for 8, which tells us that we've got 8 electrons in our valence state. Noble gas, spelling wrong. Noble gases are inert. They're already in the NS2 and P6 state. They're happy. We don't want to remove and we don't want to add. That's going to take energy, and it's going to increase the energy of that element. So let's think about this with an example of an actual reaction. So I've got this this example here. It states that lithium metal reacts with nitrogen gas to yield lithium nitride. So that's lithium metal. This is the stuff in your batteries that can react with nitrogen gas, which actually has huge implications for experimental work, because it means that you can't work with lithium and nitrogen, otherwise it forms this lithium nitride material, which is not good for batteries. And the question is, what noble gas configuration does nitrogen have? So we can look at this compound and we can assign some oxidation states sort of right off the bat. We can say that lithium, well, we know where's lithium? It's in group 1A. What does lithium like to do? Well, it likes to dump 1 electron to become noble gas configuration, right? So in that case, this becomes lithium plus, which means we have 3 plus coming from these 3 lithiums, which means that this must have this must be nitrogen 3 minus, which makes sense given where it is in the periodic table, because this would be -1, -2, and -3. So that requires us just to write out what the electron configurations of these things are. So we've got lithium 0, that's going to have a noble gas, or a configuration of 1s2, 2s1. We're going to steal that one electron, which is going to make this lithium plus 1s2, 2s2. That's a nice noble gas configuration. We're going to do that 3 times, right? So because we've got 3 electrons, I should balance this, 3. And if this happens, if we do this 3 times, then those electrons have to go. This is actually a redox reaction. They have to go to the nitrogen. Sorry, this would be 1/2. So in that case, the nitrogen is going to take on this nitrogen 0 will have a configuration of 1s2, 2s2, 2p3, and we are going to tack on all 3 of those electrons that we just stole away from 3 lithium atoms, and that's going to give us the N3 minus that we had already concluded was going to be the case, and that has a configuration of 1s2, 2s2, 2p6. Look at that. It's got a nice octet here, just like our lithium does, which achieves the noble gas configuration of neon. And so both the lithium and the nitrogen in the compound of lithium nitride have achieved their octet rule. That's no coincidence. That's the reason why lithium nitride forms, is because it's much more stable. If we start with lithium metal here at an energy, and we have nitrogen gas, and this is the energy that we start with, when those 2 things come together and react, that's going to be a net decrease in energy when we get to the lithium nitride compound, right? That's a happier state because we started with lithium 0 and nitrogen 0. Those aren't very happy. They're not in octets, but by the time we're done with the reaction, both elements are now octets. And what kind of bond would we call this? Would this be covalent, or would this be ionic? This would be an ionic bond because we are binding a metal, the lithium, to a nonmetal, nitrogen. And remember, the definition of an ionic bond is one where electrons are given away. That's exactly what happened. The lithium dumped 3 of its electrons, meaning it was oxidized, and it gave them to the nitrogen, which means the nitrogen was reduced from 0 to 3 minus.